This engine will be the same rotating speed or the same
No,
thrust.
very different rotating speed. There are a parameter called loading, disk loading, or so on. And this parameter must be same in real aircraft and in model. But for small propeller, we need a very high RPM. For example, 10,000, 20,000 of RPM. But in real engine, sometimes RPM lower than 1,000. So 10, 20 times more RPM in model than in real engine for same disk loading factor. So there are three ways to power this propulsion simulator. First one is electrical engine. Second one is hydraulic. And last by compressed air. And in Antonov facility, we use compressed air to run simulator. I don't know about this European facility, maybe also compressed air, maybe electric. Maybe this element of picture is the pipe for air. But there are possibilities that this simulator is electric. At this picture, also different type of propulsion simulator. There are for turbofan engine, turbofan, turbojet, also with very big RPM. And there are also different pictures. It is schematic. This one. Yeah, device in back for first picture used as balance, steam type of balance. It measure torque. But if you ask about wires in this part of these wires, so this wire mostly for control engine speed, rotation. But in this picture,
The first in the wind tunnel.
in wind tunnel, this device, yes, blue one.
Yes, the red one and blue one.
This device for measure forces that act on model, lift, drag forces, and roll moments. This device
Okay.
equipped by electrical sensor, tensor sensor,
Mhm.
and when forces act on this tube, conductivity of this electrical sensor changes.
So this device will be better the Antonov use wire.
Maybe, but there are problems with temperature. When temperature
Oh
change,
yes.
and there is a necessity for calibration. But this
Yeah.
device less influenced on aerodynamic. In Antonov, we see have wires, yes, and these wires
Yes.
connected with mechanical system, and these wires ADD drag, ADD turbulence in flow, and then
So the turbulence after the wire will mm, give the data some error, right?
yeah, but this device located behind the aircraft, and any turbulence that created around this device don't affect on the model. So maybe this system better, but they are very costly. And
Yes.
creation of measurement system, it's very costly and very elaborated task. And when you have working device, there are no necessity to change it to another type. When you develop a new wind tunnel, you need to select better device. But if when you have a working wind tunnel, you don't need to change working device to another type because very elaborated task to calibrate all these sensors. So, and when this propulsion simulator works, they change airflow around wing, and the coefficient of models, lift and drag, also changes. And there are relation between rotation speed, between disk loading and increment in drag and lift. So I want to see short picture. You see now picture, yeah?
Yes.
This is a Airbus A380, and half picture is real aircraft, and half picture is a wind tunnel model. In real aircraft equipped by real engine, this sketch. And in this picture, in wind tunnel, there are two different parts. This is a nacelle without any engine, just circular channel. Yeah, and this is a propulsion simulator driven by compressed air. This red part of picture show us a flow of compressed air, and there are a pipe from outside of wind tunnel. They constantly supply compressed air into model, and from by wind, this compressed air go into core of this simulator. There are turbine, and turbine run front part of simulator, a fan. And this simulator mimic real engine. They need to give same parameters of jet as real engine. We cannot simulate hot air. We don't have so temperature inside, but we can simulate speed, pressure, and so on. And this circular channel also important because this part of aircraft affect on lift and drag of wind, and also this part affect on the pitching moment. For example, do you hear about Boeing 737 MAX incident in Indonesia and Ethiopia? There are a change in engine. In new model of Boeing, they put a very big engine, LEAP, with bigger and wider this nacelle. And this bigger and wider engine nacelle changed pitching moment of aircraft. And aircraft became unstable at high angle of attack. And for compensation this instability, they put software inside. Not to they could increase tail and remain stability at same level, but they don't want increase tail because tail increment in tail area also increment in drag, and in fuel efficiency will be lower. So they think we just put software in the loop which slightly change control system, and this system put aircraft nose down when angle of attack will be a very big. But there are problems with sensors, and where in case of low angle of attack, system thinks that angle of attack is very big and put nose down, and pilot don't understand what's going on, and two airplane crashed down. And this chain of accidents start from increment of engine metal. So properly simulation of engine is very important for aircraft design. So about disk loading factor, I think we can do small sketch. For example, this wind. And we have a turboprop engine in front part of wind and a propeller. And this propeller increase speed of air. Yeah, when it creates thrust, it increase speed of air. So in part of wind, in this part of wind, we have a speed of air, a bigger speed than in round air. So for example, this is the speed V1 and this is speed V2, and this speed sufficiently more than V2. And what we have from this, we have increment in lift and increment in drag, because lift and the drag forces have speech term in their formula. For example, lift coefficient, I use Russian system of notation, but it's exactly same for English system, by S area and times air density squared speed and divided by 2. So when this term increased, all lift also increased. When this rise, this total forces also rise. Exactly same for drag. We have exactly same formula, just different coefficient. But these terms exactly same to the both formula. So when we have increment in speed at part of wind, we have increment of both lift and drag. Also increment in pitch and moment sometimes. And there are another issue. Clear this picture. For example, typical turboprop aircraft, and the speed of air in this tube increased, but we have also tail. Yes, tail surface. And when this tail surface immersed in part of air with increased speed, there are changes in efficiency of tail also. So it's a matter for aircraft stability, the influence of propeller slipstream on the stability characteristics. And this influence depend on aircraft configuration, depend on flap setting. For example, when you have wing cross section, and this is the engine, and this is a flap. So we have propeller, and when you flap down, these slipstreams change angle. And when you flap up, there are another angle. And for example, when you have tail surface in this part, in first setting, slipstream influence it on tail, but in second system, when flap down, slipstream go highly behind tail. This difference. So it's very important to test engine influence at different flap settings. Also, it's very important different side slip angle when there are engine out case. Yeah, in AN-72 there are very interesting effect. They used mutual influence between flap and engine slipstream for increase of lift. Yeah, but AN-72 have T-tail configuration and tail surface highly above that stream in edge flap setting. But there are engine out case. Take a look. We have aircraft. It's a wing, fuselage, tail surface. Very bad sketch, but we have one engine in engine out condition. So does only one engine produce slipstream? And there are asymmetry. This engine produced thrust, but this engine produced only drag. So exists a moment, and for compensate this moment, pilot need to deflect rudder, rudder and ailerons. So there are side slip angle beta, and different side slip angle. There are influence between side propeller slipstream, and in this high beta, high this angle, side strip, side propeller slipstream. Washed fuselage rear part, and from this interaction between propeller slipstream and rear part of fuselage rise new forces, and these forces change also these moments, because in this part there are difference in airspeed of fuselage in this part and in this part, and this difference of speed create additional forces, and when slipstream go to rear part of fuselage, and rise a new additional forces that tend to turn your aircraft more. So you have one turning forces from thrust asymmetry, but you have an increment of these turning forces when slipstream affect on rear part of fuselage. And this is also very important to test aircraft in wind tunnel in asymmetry flow in engine out case. Oh, okay, about 172. This extra lift depend on two factors. Firstly, it's about depend on part of wing, how many area of wing immersed in jet stream. So in case in AN-72, we have only very small part of wing. There are also a part of rear part of engine, we have a flap or the change direction of jet stream and slightly increase this part of wing. For example, there are another aircraft that have not one engine per left or right section of wing, but in Japanese Q-stall and in American aircraft, there are configuration with two engines per wing. And in this case, there are sufficiently more incrementing area. And I have an article about the Japanese aircraft. Firstly, I show you a picture from internet. Wait a minute. It's from Kawasaki. Only single aircraft was built.
Kawasaki C2.
Yes, Kawasaki C1, but highly modified. C1 have an engine below wing, but in modification Q-stall Asuka, they put 4 engine at aircraft. And they put additional improvements in aircraft configuration. Yes, this aircraft, only one was built. They take some test, but after that they put in museum. Kawasaki C1, yes. And 4 engine,
So that copy from
not 2 as in Antonov, but 4. So area of wind that immersed in jet stream increase and increase lift. But this is a very very big cost of this experimental program. At Japanese government don't want to put money in this program. And this is a rear part of aircraft. Maybe I can put full screen. Yes, this aircraft, and you see jet exhaust nozzle, very wide and not so tall. And there are another interesting part. This is a vortex generator. They added small vortex generator.
vortex generator.
Yeah, vortex generator. And this device ADD turbulence level. And this turbulence level, incrementing turbulence, prevent stall. So I made some sketch in future. And look at different flaps. They have inner flaps that works with the jet stream, and they have outer section of flaps, and this outer section have a slots, yeah. But this
So the
slot with
flap,
slots, this section of flaps have slots, but inner have no slots. That constantly surface, constantly change curvature, but they without slots. But this section have slots, a lot of slots, maybe 1, 3, 1, 2, 3, 4, 4 slots, maybe. A very interesting configuration. So what about vortex generator? I need to do a small sketch. So we have an engine here with about C2. I think it's very interesting aircraft. I seen a lot of photo. But they unable to sell abroad this aircraft. Maybe there is no market for such aircraft because there are American C-17.
yeah, only sell to themselves.
Wood and flap. This configuration have a flap. And when flap deflection engine is very big, there is a separation. Jet stream from engine, unable to turn big, and separate from surface here. And there are some turbulence. And lift decrease. For prevent this separation, they put small vortex generator. And this vortex generator increase energy of boundary layer and prevent this stall. What about principle of working? Look at this. This is the surface, and this is the speed profile boundary layer. And when there are a drop in speed in near surface, like this, or when reverse flow. Reverse flow is a separation. So when there are small, big speed, small speed, zero speed, and reverse speed. And when you have reverse speed in boundary layer, it's a separation case. So to prevent this separation, you can put small vortex generator at small angle to airflow. Yeah? When you look from above, they put not parallel to flow, they just put a small angle. And there are a vortex. So this vortex increase speed in this part of boundary layer. So before vortex generator we have small speed, after there are increased speed in this part. And when you increase this speed, it prevent separation. So it's a method to increase angle of attack for wind, to increase flap deflection angle, to increase radar efficiency by put small. In also another term, turbulizator. There are difference between usage of this term. When you speak about large one, peak, you use term vortex generator. When you speak about small one, you use term turbulizator. So just return to internet and I show you a picture of, oh, maybe we don't need another picture. We have an aileron here, outer section of wing and internal section.
Yes.
And in outer section also exists vortex generator. These small dots, it's same device, but this device not so big like this. This a very bigger, this smaller. And when you look at wing of Boeing 737, there are also exist small vortex generator. And this vortex generator increase efficiency of aileron at high deflection of angle. Yeah, this is a 4-engine configuration of similar to AN-72. There are another aircraft from NASA.
I have questions.
I forget properly name. We need to use general term, upper surface blowing, or USB, like flash USB. When inside wing stall before outside, it's possible, yeah. What Google show us? Yeah, this picture, this 4-engine. Similar configuration. This is the Canada-made aircraft, C5 Buffalo or so. NASA Boeing Wheat. I don't remember proper name. But they also use 4-engine. And test this aircraft, very extensive program of test, but they don't put this in serial production too. This only for experimental. But area of wing that immersed in jet stream sufficiently larger than in Antonov 72. So I also have an article about wind tunnel investigation of Japanese aircraft. Maybe I able to find it. But I forget in what folder I put this PDF file. But in this PDF, there are a graph of lift coefficients from engine, how much lift they did this configuration to aircraft. And as I remember, there are a number like 4, 5, CL equal 5. Not 1, not 3.
CL equals 5.
Lift coefficients here. Lift coefficients, but we need to find this article. Maybe I put it in this folder. This folder about high lift device, about flaps, and maybe no, I don't see it. This about on this. Look at this, for example. This about upper surface blowing. Maybe about Japanese, but I don't. So mostly increment depend on two factors: how much speed produce of your engine. Of Prussia, this is some from Germany, maybe. If you see any graph,
Well,
no,
top
this
secret.
yeah, top secret. No, this is not maybe this NASA calculation of something. No, also not this picture. Maybe this is graphic after part of document. Lift moment, lift coefficients, for example. So, and we have experimental point for 6, yeah? Lift coefficient equals 6. And
This angle is for wing or for flap?
two engine
degrees.
model, USB model without tail, only wing and fuselage and engine, and flap deflected at 30 degrees. And there are 4 different curves, yes? Different experimental with different coefficient CJ. This coefficient CJ, it's about speed of jet from engine. In case of 0, we have no influence of engine, and we have lift equal maybe 2.5, yeah. But when they put engine on, lift increase and sufficiently increase, and we have 6 and more than 6 in this case. And maybe we need a sketch of this model, how it designed, what configuration they use. Maybe this is about same aircraft from NASA. Yes, we see wing, we see 2 different part of flaps, inner flaps and outer flaps, and this for engine. This about some method of calculation, but I don't see model from wind tunnel. No, this don't show us wind tunnel model. So I don't know what about aircraft it is. So maybe I need to look about Japanese name in.
Where can I download the file like this?
What you want to read this file? Yeah, I can put it in chat.
Okay, thank you.
Oh, there are also Russian book about different method of increment of wing lift. Petrov, энергетические методы увеличения подъемной силы. So energetic methods of lift, wing lift increment. So maybe there are some picture about configuration like AN72. No, this book don't contain information about this. So it's possible to obtain lift like 6. So 3-fold increment. We have 2, slightly more than 2. But in maximum power of engine, we have 6 and bigger than 6. So up to 3 times increment in lift.
So this aircraft can use the small area of the wing
yeah,
to
small
reduce the
airstrip,
drag.
and from aircraft carrier, it can fly it from very small airstrip and very small speed. And in end of 20th century, maybe in 80s, military of different countries will want to develop aircraft for very short takeoff. They think in case of future war, enemy put a bomb in middle part of airstrip, and typical airstrip like 3 kilometers, yeah. And when you have a bomb crater in middle of your airstrip, you have only 1 kilometers without any obstacles, yeah. And military,
Short takeoff, short landing.
yeah, they want to aircraft, they can take off from half of typical airstrip. Like this, typical airstrip. Enemy puts have bombs in middle part, and this all what remains for your aircraft, and your stall aircraft must be able to take off from this small part. So this needs a very high lift coefficients, not 2, 3 in typical aircraft, but 4, 6 and more. And one method to obtain this lift to put engine in upper portion of wing. There are another methods, and after small pause, I tell you about different method. Okay. We have end of time in our Zoom.